So I want to use these spectral sequences that we've been developing, but in a non-trivial setup. So let's take. So we're now going to have to talk about shapes, and since not everyone needs to know about this, let's just set up that. So X is going to be a topological space. And F is going to be a presheaf of sets. Although I'll only use abelian groups today. So let's say of abelian groups. On X. So this means that for every open inside of X, you have an abelian group f of u. So let's say that's an abelian group. And for every pair of opens V included in U, then you have a restriction map that's a morphism of abelian groups. So that's the restriction from U to V, from FU to FV, which is a morphism of abelian groups. And these restrictions are supposed to satisfy an identity. That is the restriction. So the case where V is equal to U, then the restriction UU is the identity on F of U. And if you have W inside of V, inside of U, then you have a restriction from U all the way down to W. But this is the same thing as restricting from U to V and composed, well, yeah, other way around. Restriction from U to V and then restrict from V to W. So that's what a presheaf is. And they form a category. A category in a trivial way. And even an abelian category in an obvious way. So that's, they form the category of presheafs of abelian groups on the given topological space X. If you give me two such objects, I want to define what a morphism of those two guys is, and that's going to be for every open U, you want to give me a map from f of u to g of u, satisfying the obvious compatibility conditions with the restriction map. So for every U, I guess a map phi in hom fg is the datum of, for every U in X, a morphism of abelian groups from fu g, compatible with or commuting with restrictions. Now, a presheaf F is called a sheaf if in addition, well, I'll talk about elements in FU as sections on U of X. So this guy will satisfy an extra condition, and that condition is that if you have a bunch of opens, say U alpha, that are opened, next open, And an S alpha is a section when U alpha intersected with V. V is some given open. V in X is some open. You can take V to be just X. But I'll need this in a second. Such that for every intersection of two of these guys in U alpha and U beta, so you can look at S alpha, which is here and restricted to this intersection. So if you look at S alpha restricted to U alpha intersected U beta intersected V, and this by definition is the restriction from U alpha intersected V to that triple intersection. Applied to this S alpha. Then we'll require that this is equal to S beta, restricted to the same guy. Then there exists a unique S, which is a section of V such that S restricted to U alpha intersected V is equal to S alpha restricted to U alpha intersected V for every O. The only condition is that V has to be included in the union of all these U alphas. So U alphas is some collection of opens that cover the whole of V. And that's what means to be a sheaf. It's just the condition that you have a pre-sheaf, but then you can glue sections. So of course, a pre-sheaf tells you that from any section in f of V, you can restrict it to each one of these U alphas, and you get a section on each one of these U alphas intersected with V. Now the sheaf condition is that if you give me compatible sections in each one of the opens, you can glue them to get a global section on the whole of V. You can take this V to be all of X. Of course, you have a functor. There's a functor, which is just forgetting from the category of sheaves on X to the category of pre-sheaves on X. By the way, just a morphism of sheaves is just a morphism of pre-sheaves. And the functor is just forgetting. You just forget the fact that you that you satisfy this condition. So a sheaf is in particular a pre-sheaf. But this functor is exact, and it has an adjoint. It has a left adjoint, which is the sheafification. That it takes a pre-sheaf and it gives you a sheaf. I think that's Harnshaw's notation, or probably some people like to write a tilde. Not going to write how to construct this because we're not going to need it, but this is a left adjoint in the sense that in the category of sheaves between F plus and some sheaf G is isomorphic to in the category of pre-sheaves between F, where you forgot this is a pre-sheaf now, and G, where you forgot that it was a sheaf. So for any pre-sheaf, you can get a sheaf out of it. We won't need this in a second. We won't need this for a while. But what do I want to do? We have a functor from the category. We have a functor from the category of sheaves on X to the category of abelian groups, which takes a sheaf F and it gives you the global sections. And I want to understand is the corresponding functor in the derived categories of these guys. So I want to understand the derived functors for this functor. So for that, I need to understand whether or not the derived category makes sense. For this is an abelian category. The category of sheaves is an abelian category. I'm not going to construct quotients. Yeah, probably I will. But I want to, even to make sense of how to compute the derived functors for this functor, we need to talk about having enough injectives. So let's do things slowly. So first of all, this category is an abelian category. Okay, the fact that it's additive is clear. So addition is just on each open, you just take the sum. So additive is clear. It's clear. You just take for each u, you take the sum of two of your guys. And this defines a sheaf. You can quickly check that that's a sheaf. Having kernels and co-kernels, so having kernels is easy. So if you have a map from F to G phi, then you can look at the kernel of phi at U to be the kernel of F of U to G of U. And that satisfies all the axioms of being a sheaf. But having co-kernels is not so trivial. So co-kernels, you try the obvious thing, which is if you give me some phi like this, then you want to define the co-kernel of phi evaluated at U to be the co-kernel of phi of U, well, of this map from F of U to G of U. And this is not a sheaf, but it is a pre-sheaf. So this thing is not a sheaf. But it is a pre-sheaf. And checking that it is a pre-sheaf is clear. You just restrict each one of these maps using the restrictions on F. And it gives you well-defined restrictions. Just the problem is that you cannot necessarily glue sections of this thing. But since it is a pre-sheaf, you can just take this F plus. So you can sheafify this. So you can look at the co-kernel in the category of pre-sheafs of phi and take the associated sheaf with respect to that. Granted, this doesn't tell you much if you already didn't know this, but there's one thing that we're going to use out of this construction, which is the following. If you have a morphism of sheaves, again, in particular, this is a morphism of pre-sheaves. That means that for every open, you give me a map like this on sections. Now, what does it mean in an abelian category that your morphism was surjective? It means that the co-kernel is trivial. Now, that doesn't really mean that the map is going to be surjective on global sections. Right? So if I look at the co-kernel and I look at global sections of the co-kernel, that is not necessarily the co-kernel of the map of global sections, because that was just a pre-sheaf and I needed to sheafify it. And so what happens is the following. The statement is that if you have a map that is surjective, then any section on G, you can find preimages locally of F. So for any global section of G on X, there exists an open cover of X by opens U alpha and sections of F on U alpha such that the image of those sections coincide with the restrictions of the section of G. So let's write that. And that's the only thing that I'm going to use out of the co-kernel construction. let's suppose, so I've just stated that the category of sheaves is an abelian category. So let's suppose that you have a map of sheaves. Phi is a morphism in the category of sheaves on X. Again, sheaves of abelian groups from F to G. And let's suppose that the co-kernel of phi is 0. So this means phi is surjective. Then for every section S of G in X, there exists an open cover of X and sections S alpha. These are sections of F in U alpha, such that phi of S alpha are equal to the restriction of S to U alpha. And if you wish, you can take that to be the definition of being surjective. Okay, so that's an abelian category. And if it's an abelian category, I can look at the derived category of sheaves on X, of sheaves of abelian groups on X. And, well, I have this functor. This functor of global sections is left exact. So gamma is a left exact functor. And we've just seen the fact that it cannot be, it does not necessarily is not necessarily right exact. Okay? So if you have a sequence like this, an exact sequence of sheaves, meaning the co-kernel of this map is 0, so it is surjective in this sense, but it's not necessarily surjecting at the level of global sections. So f of x is still injective into g of x. This guy is still exact into h of x, but that's it. But anyways, we've defined generally, whenever we have an abelian category, and we have a left exact functor, we already know that we have these functors, which are exact at the level of triangulated categories. From D plus, or D minus, or D bounded sheaves, so that's the derived category, to the derived categories of abelian groups. Again, plus, minus, or bounded. So this functor is an exact functor of triangulated categories. But there's no way we can, so the only way we know how to compute that functor is if we have enough injectives or if we have enough objects such that homes in that derived category are actually homes in the homotopy category that were actually maps of complexes and not just roofs of map of complexes. So for that, the statement is the following. The category of sheaves has enough injectives. So let's prove that. Okay, so before doing this, we need a couple of constructions. So let's start applying functors between different topological spaces. So this, I want to prove this today, and I want to prove something stronger today. So first of all, if you have a map of topological spaces, a continuous map of topological spaces, then you can push forward sheaves. So if you have there's a map from sheaves on X to sheaves on Y, which is given as follows. If you give me some F, which is a sheaf on X, you push it forward to Y. Now this is supposed to be a sheaf of abelian groups on Y. So if you give me an open is U. U is an open on Y. Since F is continuous, F inverse of U is open in X, and I can just take sections there of F. So that definition satisfies all of the axioms of being a sheaf. So that's a sheaf. Similarly, F inverse, I guess I should write it this way. F inverse goes from sheaves on Y to sheaves on X. This is a little bit trickier because now you start with an open U in X, and you want to evaluate this sheaf on this open U. And, well, you might be tempted of using F of U. So you have this open on X, you apply F, which goes from X to Y, it gives you some subset of Y, and you take sections F of that. But the problem is that this is not necessarily open. The map F that you started doesn't need to be open. If the map that you have is open, then this will give you a sheaf. But if the map F does not send open to open, then this doesn't even make sense. I've only defined F on opens. So I cannot do this. But what I can do is take F of V for some open V. So I can take F of V for some open V. And what is the condition on the open V? Is that it should contain F of U and be open in Y. I'm sorry. Yes, that's correct. Open in Y. So I started with F as sheaf on Y. I look at all the opens in Y that contain F of U. I evaluate F on that V. Now, this is a directed system. If I have V that contains F of U and it contains some W, and both of them contain F of U, then any section on F of V I can restrict to F of W. So guys like this form a directed system, and I can take therefore the limit of those. These are all abelian groups. All the restriction maps are maps of abelian groups. So this is a well-defined guide. This is a well-defined abelian group. The problem with this definition is that it doesn't give you a sheaf. It gives you a pre-sheaf. So take the associated sheaf to that. The sheaf associated to this. So this is that. Okay, so those are two functors. I hope that I won't need them except in the cases where these two functors are trivial to compute. But they are adjoint. These are adjoint functors. So F inverse is left adjoint to F push forward. In particular, this means that if you give me maps, humps in sheaf of X. So F is a sheaf on Y and G is a sheaf on X. Then these are naturally isomorphic. Sheaves on Y between, what did I do? Yeah, that's correct. This holds for every, and this is functorial in F and G, and this holds for any F which is a sheaf on X, on Y, and G which is a sheaf on X. Now remember that if you have an adjunction, this equivalent, having this adjunction is equivalent to having a pair of maps canonically for any object. So this is that you have a map from G into, I'm always horrible with this, with the order of these things, but I think this is correct. So F inverse of F push forward to G. Or did I do this incorrectly? And I just did it incorrectly. Is it? I guess here's F, and here's F. And I have a map from F inverse, F push forward of G to G. But I want to understand this map. And I want to understand this map in only one case, which is the case where X is just a point inside of Y. So we can apply this to the situation where this is just a point. I guess it's like this. This is the topological space X, which is inside of the topological space Y by any map F. I'm going to call iota this map now. It's just a point. Okay? So it sends this point to a point. Let's use that little letter X here. Okay. So I have this F, which was a sheaf on Y. And I want to understand this restriction. And let's look at the definition here. So what is, so I have some sheaf F here. What is iota inverse of that sheaf F evaluated on an open V? On an open U, I guess, of Y. And then I immediately see something that, let me not write as braces. This is 0 if X is not contained in U. If X is not contained in U, I can just take opens inside of U. And I'm pulling back this sheaf F to X. So what I'm doing is I'm taking a limit over all opens that contain the image, and there's no such thing. So I guess this is stupid, the way I'm writing this. So let's write this correctly. This pullback is into an open set of this guy, and there's only two open sets that I can take on this topological space. I can take either this open set, or I can take the whole open set, which is the whole space. So there's only two spaces, and then the preimage of the empty guy is going to be empty, of course, and the preimage on X is what I'm interested in understanding. So there's only two opens. This is just 0, because F of the empty space is the empty space, and the limit of all of these sections is going to be 0, which is the terminal guy. But then the preimage of F evaluated at the point, at this total space, which is just X, which is open. This is, by definition, the limit over all V's that contain F of X, which is the little point X of F of V. And this is what we want to understand. This, I'm going to call it F sub X. This is an abelian group. And that abelian group is, well, it's given as that limit. So what is an element here? So an element S in F of X, by definition, is an element of this colimit. And an element of this colimit is, well, it's just it's a pair, V as V, where X is a point in V, which is open in Y, and SV is a section of F restricted to V. But it's the equivalence class of such things, where if you have another W and you have some SW, and again X is inside of here, same conditions, then the restriction SV restricted to U, to V intersected W is equal to the restriction of SW restricted to V intersected W. Then we say that these two are equivalent. So equivalence classes of those are these elements in this Fx. This is called the stock of F at X. And these are the values of this pullback of F to the point when evaluated on the full space. So now I look at the push forward of that sheaf. This is a sheaf on the point. This is a sheaf on the point that has this abelian group as global sections. So it has no sections on the empty set, and it has this abelian group in the whole set. Nothing else. So what is the push forward of that sheaf? So what is the push forward of that pullback of the sheaf F? Now this is a sheaf on Y again. And now by my definition of the push forward, this is much simpler than this direct limit. What I need to do is take an open in Y. And I say, well, it is my sheaf, which is the pullback, evaluated and the preimage of that open. And the preimage of that open is very simple to see what it is. It's either the whole space if X wasn't U, or it's nothing if X was not in U. So these are my two options. And I see that if X is not in U, this is 0. And if X is in U, this is Fx. So this is a sheaf in Y. And we see that we have a map of sheaves from F to that sheaf. So for every point in my space Y, I have a map from my sheaf F into this push forward pullback of F. This iota depends on X. So what is this map? Well, if you give me an open U and a section, so for every open I need to give you a map from F of U into this either 0 or Fx. Okay. So to either 0 or Fx. So this is very simple. If X is not in U, then the map is 0. There's nothing else I can do. But if X is in U, I need to give you a map to Fx. But any section here, I can send it to the pair U, S, the class of this pair in that direct limit, which is an element in Fx. Now, this is clearly a surjective map of sheaves. Because so with our definition of surjective, let's take a section of this sheaf. Let's take a global section, or let's take any section of this sheaf. Any non-trivial section of this sheaf is a global section. It's a section of the whole space. This X is in the whole space. And it means it's just an element on the stock at X. And for any such section, there exists one representative. So that means one open U and a section that open for that sheaf F. So that's it. That's a representative. That's an open covering. Just extend this to any open covering. It doesn't matter where it is. And you have sections, a local section that maps to the section that you're interested in. So this is a surjective map of sheaves. So this is exact. And what is the kernel of this? So the kernel is something interesting as well. Do I need the kernel or not? Perhaps I want to give it as an exercise, but it's an interesting exercise. So let's understand the kernel. And this is in general. It doesn't need to be a point inside of Y. So this works for any subset. So let's do this in general. I won't have time, so let me state it. Let me say that U is going to be Y minus the point X. This is open. If my topological space is T1, for example, then points are closed, and that thing is an open subset of my topological space, although I don't need this guy to be open now. But that's typically the situation where we're working, where points, closed points, single element points in our topological spaces Y are going to be closed. So this is an open inside of Y, which is the complement of X. So this guy is the complement, let me call this J, it's the complement of iota. Now, if we have a sheaf on Y, I already told you how to restrict to some subset, to some subspace. We have this sheaf on U. It's a well-defined sheaf on U. When our U is open, this is much easier and doesn't require a direct limit. As I already told you, this map J is open. It sends open in this topological space to opens in this topological space. So I don't need to take any direct limit. If I want to check what is the direct image, what is the pre-image of this sheaf evaluated on some V here, I just look at F of V intersected with U. And those are the sections of this sheaf. And this is a sheaf on U. But what I can do is push it forward in a different way to F. So let me tell you what this functor is. If you're given a sheaf G, is a sheaf on U. Well, let's say the G is a sheaf on U. Then this guy on G is going to be a sheaf on Y that is defined as follows. You'll declare it to be valued on V to be just the values of, so you want to extend this sheaf on U by 0. So I'll declare this guy to be the, on Y to be my G on V intersected with U. Okay, so this is the kernel of that map. So you have an exact sequence. There's an exact sequence. I might need it in a few days, so. I guess I'll do F to F to the push forward of the pullback of F. And this is a sequence of sheaves on X. Well, sheaves on Y is what I'm using. So this is for any point you have this. So this is a sheaf that has support at the point X. The support meaning that the only stock of that sheaf that is non-zero is the stock at x. And the stock of this sheaf at x is just fx. Any other stock of that sheaf is 0. And this sheaf here has support on u, which is the complement of that. The stock of that thing at x is 0, and the stock of that thing at any other point is equal to the stock of f at that other point. Okay. Why is all of this? Why is all of this? Is because I can look at these sheaves, and I can look at these surjections that I have here, and this is a surjection for any x. But I do get an injection into the product of all of those. So what I can do is look at the product of all of those sheaves. Why? This is going to depend on the point x, so let me write it x, y, x inverse, and here push forward of f. This is for every point x in x. So let's put a name for this sheaf, perhaps. Let me call this sheaf f lower x is a stock, so perhaps f upper x. So this is the product over x of f upper x. And this map is injective. An injection of sheaves. So first of all, the product of sheaves is a sheaf that's trivial. But, well, it's not entirely trivial, but it's easy to check that the product of sheaves is a sheaf. So that's a sheaf. But the fact that this map is injective, well, we've seen that injections can be checked now at the level of stocks. So, well, it doesn't matter. If you just grab any section here that goes to 0 there, it means that on every point, the image of your section was 0. So if you have a section that for the image on any stock is 0, then your section was already 0. So that's the axiom of sheaves. Because you could find a covering where in each one of these local coverings, the 0 section is the image of your section, and now you glue those little germs into a section that coincides with yours, just by the axiom of being a sheaf. So this map is injective. Okay? But now, okay, so that's one thing, that map is an injection. The other observation is that fx is an abelian group. So this is the sheaf on the point. This is just an abelian group. And abelian groups have enough injectives. So I can find an injection of abelian groups. Another thing to notice is that the push forward for this closed embedding is actually exact. It's left exact always. In this case, it's exact. It doesn't really matter. We're going to prove it anyways. But this already says that if I look at the push forward of these things under I, so by definition, I get fx. And now I'm going to map it to I push forward of this. And that this is going to be injective. So let's prove that this is injective. So let me put a name to that. This is going to be I sub x. So again, what is this sheaf? This is a sheaf on y that is either 0 if x is not in U, and is all of ix, which is an injective abelian group. That's just a divisible abelian group if x is in U. So I claim that that sheaf there is injective. Well, so we take some G, a sheaf, an arbitrary sheaf on Y, and so I want to claim that this sheaf here, which is a sheaf on Y, is injective. So let's take a morphism from that guy into that sheaf. But now by adjunction, this guy was a push forward. This is the push forward of I lower x. And if I have a morphism like this is the same thing as having a morphism from the pullback of G to fx, to the point x, into Ix. Remember, the pullback is left adjoint to this push forward. But this thing here, as a sheaf, is just the abelian group, which is a stock, which is G at x. So having a morphism from G to I supra x is the same thing as a map from the stock of G at x to Ix, which is this thing, which is injected. So now let's suppose that you have a morphism from G to Ix, and you have a morphism of sheaves from G to H. So this is a sheaf, this is a sheaf, and this is a sheaf. These are all sheaves on Y. Okay. So what we've seen is that this guy here comes from a morphism from G of x to Y of x, which is injective. And any morphism from H to Y of x is going to factor to a morphism from H sub x to Y of x. Now, this thing here factors through, therefore, this map. And since this guy is injective, then I have a map from G sub x to H sub x that makes this diagram commute. Okay, so what I have is, at the level of abelian groups, I have the restriction of these maps to the point, gives me a map like this. So this is just applying the pullback to the point. The restriction of this map to the point gives me this map, and this is now a diagram of abelian groups, and this is injective. That means that this guy exists, making this diagram commute. Now push forward that guy. So a map like this, by adjunction, is equivalent to a map from H to I sub x, supra x. So that shows that this guy is injective. And the product of injectives is injectives. So that means that the product over all x of I x is injective. And that shows that f is inside of this guy. And this is an injective. Good. So at least we have a candidate to compute derived functors, because we can embed any sheaf of abelian group into an injective sheaf of abelian groups. I mean, those are too large, so we need more interesting sheaves. But at least now we know that we have injectives, which are good. So now we know how to compute the derived functors to global sections by just finding to our sheaf a quasi-isomorphic sheaf by injectives, so a resolution by injective sheaves. Now that we know that we have enough, we just can apply the general machinery of constructing a resolution of our sheaf by injective sheaves and applying gamma to that, applying the functors of global sections to those. So let me give you a definition of a slightly better class of sheaves. A sheaf is flabby if restrictions are surjective. Open implies that the restriction map from U to V from f of u to f of v is surjective. And lemma, injective sheaves are flat. So now, what did we gain by constructing injective sheaves? So remember that we have a general theory for the derived category. So we have this functor gamma that goes from sheaves on X to abelian groups. And R gamma goes from the derived category of those. And now I'm going to be looking at the bounded derived, at least bounded below derived category of sheaves on X. And it goes to the bounded derived category, well, the bounded below of abelian groups. And the way we apply this, we can compute this guy now by, if you give me a sheaf, find an injective resolution of that and apply gamma to that. That was a general theorem that we have. So now, what we've gained is that if I define HI, this is a definition, HI of my topological space X with coefficients in a sheaf F, by definition, is the derived functor I times of this functor gamma on X of applied to the sheaf F. Which we know that we can compute this as the ith homology of the functor gamma on X I for I a resolution of F. This is a quasi-isomorphism. But in particular, out of this, we know that HI, well, H0 of XF is just the functor gamma, which is left exact. It's just global sections of XF, which is just F of X. But also, we know now that HI of XI is 0 for every I bigger than 0 and I injected. Those are the two things that we had for free. So now, let's try to prove that flavies are going to be good to compute derived functors in these categories. So, okay, so I want to prove that injectives are flavi, that they satisfy this stronger condition than just being injective. And all right, so the first observation is this. Let's suppose that you have a short exact sequence of sheaves in X. And let's suppose that F is flavi. So let's look at the long exact sequence in homology. Okay, I'm going to prove something because I already started. So let's look at the long exact sequence in homology. So the next term is going to be H1 of XF. So these are all H0s, global sections. The next term is H1 of F. And it continues with H1 of G and so forth. So let's analyze this thing. So I claim that this is 0. I want to prove that this is 0. And before doing so, let's suppose that we have a section here. So I cannot pull it back to G because, well, we know that the functor of global sections is not exact, it's left exact. So it doesn't necessarily, there doesn't necessarily exist a section of G of X that maps to S. But what we do know it exists, there exists a covering of opens in X and sections S alpha of H. Yeah, probably I should use a different letter. So let's use T alpha, sections of G of U alpha, such that the image under this map, pi of T alpha, is equal to the restriction of S to U alpha. So that was the fact that this map is surjective as a map of sheaves. So those I can pick here. So I have these T alphas and my covering U alphas that cover these guys. Okay, now what I could do is I could restrict my sheaves to U alpha. So what I recognize is the following. Yeah, perhaps. Just a second. Well, I'm going to restrict F to U alpha. So this restriction is just the pullback under the inclusion of U alpha into U. And I can restrict my G to U alpha. So this T now is a global section of this sheaf on U alpha. And this, well, it doesn't matter. Now, here I'm going to have some sheaf, let me call it H bar, it doesn't matter where it is, which is, it's going to consist of restrictions of H to U alpha. But I'm just going to define it to be the co-kernel of this map. And so this is an injection of sheaves. This is the restriction of F to U alpha. This is the restriction of G to U alpha. And this, by definition, is just the co-kernel of that one. Now, the T alpha that I have here is a section of U alpha that maps to this restriction of S on H on U alpha. So that's the T that I constructed there. I claim that this S here has to map to 0 here. So let's see why. And perhaps I should do this in 2 steps. So let's do a few things before. Let's do a few lemmas. So first of all, given an open U in a space X, I have a functor. I have a functor from sheaves in X to abelian groups that sends the sheaf F, and it gives me, this is a sheaf on the full X, and it gives me back the global sections on U, the sections on U, this F of U. This is a well-defined function. If you give me a sheaf from F to G, and a morphism from F to G, then for U in particular, you're going to get a map from F of U to to G of U. So this is a well-defined functor from sheaves to abelian groups. This is a representable functor. Namely, there exists a sheaf. Let me put a name to that sheaf. I'm going to call it ZU. This is a sheaf on X such that hom from that sheaf to F is F of U. And this is in the category of sheaves on X. So that is to be a representable functor. My functor sends F to F of U, and I'm finding an isomorphism of functors between that functor and the functor that is just homs from that object Z of U. So let's construct that sheaf. So this sheaf is a sheaf such that if you give me an open V in X, which is open, then this ZU on V has sections Z if V is contained in U and 0 otherwise. So that's a sheaf. So now, I want to prove this statement, that there's a natural isomorphism between functors, hom ZU dot and sections on U. Okay? So let's suppose that you have a morphism of sheaves from ZU to F. Well, if you have such a morphism of sheaves, then you look at phi on U. In particular, for U, it should give you a map from ZU of U into F of U. And this guy is, by definition, Z. This is actually equal to Z. And Z has an element, which is 1. So the image of 1 is a section in F of U. So for any phi, I can give you the image of 1 in F of U. How about the inverse? If you give me a section of F of U, given S in F of U, then you obtain a unique morphism of abelian groups from ZU of U, which is Z, into F of U. And that just gives you the restrictions to any V. For any V that isn't contained in U, you just restrict that map. So this is this isomorphism here. Okay, I want to exploit this into proving that any injective sheaf is Flavic. So let's suppose that you have an injective sheaf I. Say that I is injective. And I have, what I need to check is that for an inclusion V into U, I need to check that I of U surjects into I of V. That's the definition of being Flavic. Right? For any inclusion of sheaves, the restriction is surjective. For any inclusion of objects, the restriction is surjective. For any inclusion of opens. Okay, but this guy here is hom, by that assumption, this is hom from ZU into I, and this is hom from ZV into I, and I'm asking that this is surjective. And this is now in the category of sheaves. This is now in the category of sheaves. But I is injective. In the category of sheaves implies this. Remember, the definition of injective meant precisely this statement. Because the fact that I have an inclusion, so remember what was to be injective? That if I have a map of sheaves like this, an injection like this, and a map to I, then this guy exists. So this is from F to I, I'm sorry, hom from G to I to hom from F to I, which is composition with this injection, is surjective. Hom from G to I to hom from F to I is surjective. This is equivalent to I being for any injection. So this is the composition with this injection. This is the definition of I being injective. So now I read this, and what I'm seeing is that I need a map from, so I need a map from G, I want it to be ZU, and F, I want it to be ZV. So what I need is a map from ZV to ZU, which is an injection of sheaves. And this is the obvious injection of sheaves. The fact that ZV injects into ZU is the obvious injection of sheaves. It's just the injection of Z into Z. Okay, so we've seen that I is injective, therefore this map is surjective, which means that this map is surjective, which means that I is Flavi. So now, let's prove. So now we know that injectives are Flavi, but we know more. The restriction of Flavi sheaves to opens is Flavi. If I have my space X, a Flavi sheaf F on X, and an open U inside of X, then I can just restrict my F to U. Again, if I call this map J, this is by definition J, I'm sorry, this by definition is J inverse of F. It's also Flavi. That's clear because if you give me V inside of W opens in U, then the sections of that restriction, so an open in U, this guy was open already, so they are still open in the ambient space X, so a section on F of this restriction on V is just the same thing as a section on V, and a section of this restriction on W is just the same thing as a restriction, an F on W, and the restriction of this guy is just the same thing as this restriction, which is surjective. So in particular, if you have an injective sheaf on X, then the restriction of that guy to any open is Flavi. But it might not be injective. But it's Flavi. Okay, so now I'll continue with this sequence. So what I want to check, I want to prove that Flavi sheaves are adapted to, so Flavi sheaves are adapted to homology. To HI, which remember was RI gamma. Or are adapted to gamma. In other words, the higher homology of a Flavi sheaf is 0. We already know this for injectives. Okay, so we started here in proving that h1 of a flavy sheaf is 0. And I want to prove that all h's of a flavy sheaf is 0. So I'm going to break this into two. I think I have time. I'm going to break this into two pieces. So I started with this, with F, G, and H being flavy. I want to prove that this map on global sections is still exact. That's going to come from H1 and X being 0. And the other thing I want to prove is that if F and G are flavy, then H is flavy. So those are two things that I want to do. So A is that, and B is that if, is that right? That's right. If F and G are flavy, then H is flavy. Okay, so let's stop from here. Let's. Okay, so here we'll need something non-trivial. Okay, so I want to prove that this sequence is exact, so that this map here is 0. And in order to do so, I'll look at the following. Yeah, I think we have enough time. So what we do know is that for any section here, we can locally lift it to G. So I will construct a directed system. I want to construct an open where a big open in G where I can actually lift the whole S. A maximal U in X where I can lift all of S. And then I'm going to find a maximal U, and then I'll claim that that maximal U has to be X. So then claim that U has to be X. Okay, so we look at pairs that we have like here. So let's do it like this. So we look like pairs. Since we have this covering, we know that at least one of them. Let's write this. We have our section S here. And let's look at pairs here of the form V, T, where T is a section of G on V, such that pi of T is equal to S restricted to V. This is a local lifting. And we know that at least there is one such pair because this map is surjective, this pi is surjective. So there's a non-trivial pairing like this. So there's a non-empty V where this, with a non-zero T where this happens. Well, no, it's not necessarily non-zero T because S might be 0. But there's a non-empty V where this happens. Now, this is a directed system. if you have some W that is included, well, that is included in V, and some TSR, a section on W, here I have some T here, then I can say that this is less than this if the restriction of V of T to W is equal to R. So this gives me a directed system of objects satisfying this condition. So by Zone's lemma, there's a maximal one. With that property. Okay? So that T is the restriction of S to U. So that's my maximal U, and I want to claim that U is equal to X. So let's suppose that U is not X. And we have some point, therefore, that is not there. Okay. So we have some point and some neighborhood of that point that is not in U. It's not contained in U. So I'm going to take that open V, which is not empty. So an open. And the trick is going to be trying to extend my section T to the whole of U intersection U union V. Okay? So this P is a point in X that is not in U, and I have some open V that contains P. It's inside of X. And what I want to do is I want to try to extend my T to a section on all of U union V. Okay? All right. So how are we going to do this? Second. We want to exploit the fact that F is flat. So U is the maximal such that G, and this is a section that maps to S there. It's fine. Eu vou pegar V. I'm sorry.
Because pi is surjective, so we can take V to be an open neighborhood of P, where we can look.
Tá certo. Eu vou pegar. Não, desculpa, it's impossible for me to switch languages. But that's right. So I'm gonna try to pick up on V. Since S is global, I'm gonna lift V. I'm gonna lift S to V, and I can make V to be small enough if I want. Thank you. That's right. So, and then we're going to look at the difference of those two. And that's going to work. So what we do is just make V as, well, this is not that V. This is the V. So I'm taking, V is a neighborhood of this point that is not in U. And take V to be small enough. So we have some T prime V such that S restricted to V is equal to T prime. This we know because pi is surjective again, as Bruno pointed out. So now we have two things, because now we can look at V and intersect this with U. And in here I have two sections. I have T and I have T prime. and they both restrict to the same thing. So T was defined on all of U, that restricts to V intersect U, and T prime was defined on V, on all of V, that restricts to V intersecting U, and they both restrict to the same thing. They both, the restrictions equal S restricted to V intersect U. But they're not necessarily equal. So I cannot claim that I have one section that extends the whole of X. But what I can do is look at in this intersection, I can look at the difference between these two. In that open. So this is a well-defined section of G on V intersected U. And this guy maps to 0. Okay. So now I can restrict F to that open, V intersected U, and I can restrict G to that open, which is V intersected U. And I have something, a section there that goes to 0. Therefore, it can be lifted to F. So I have a section, STR, in F of V intersected U that maps to that. So if I call this guy iota, such that iota of R is equal to T minus T prime. Okay, but the thing is that F is flabby, so I can extend this to a global section. I'm going to call it R anyways, but this is a section of the full f of x. So here we use that f is flabby because the map from f of f to f of u intersected v is surjective. So the preimage of R is what I'm calling R again. So that R is something that restricts to that T and T prime. And with that R, with the image of R, we can add to T. We can just add the image of R. Probably it needs to be minus R. But the whole thing is that with this R, which is defined on the whole of V, you can get. So whatever I add to this R, this thing here maps still to the same S. Maps. Well, is the restriction of this to U union V is equal to the restriction of S on U union V. And this is just because the restriction of R on that intersection is 0. And this is absurd. And this is absurd. Okay, so that shows that, well, because U union V is larger than U. So that shows that this being flabby makes this sequence exact. It hasn't shown that this guy is 0 yet. It's just only shown that this sequence is exact. So we know now that we have the following sequence exact. F of x to g of x to h of x to 0 being exact. Okay, so I wanted to prove this. I wanted to prove that all the higher homologies are 0. Yeah, okay, so let me tell you what I'll do next time. I was supposed to do all of this today. So next time I'll finish the proof that all the homologies are 0, and I want to prove the following. I want to prove Serre's vanity theorem. This is what I'm aiming to prove. Theorem. That X be an affine scheme. So that's the spectrum of a ring, and F be a quasi-coherent sheaf on X. I want to prove that the sheaf homology of X with coefficients in F is 0 for every I bigger than 0. So all of this was preparation, and I haven't even talked about sheaves of modules yet. I'm only talking about sheaves of abelian groups so far. So the next time I'll finish with this proof that the higher homology of Laplace sheaves are vanished, and then I'll start with this the preparation for Serre's theorem.